everyone, welcome again to Modeling Methods in Mechanical Engineering, and today we're going to start a new section of the semester in which we're going to concentrate on the solutions of partial differential equations, both analytically and numerically. Now, we're going to start with analytical solutions using some of the original techniques to solve these equations, and in order to understand how these methods and techniques work, we need to understand how a very specific class of ordinary differential equations work, because these techniques to solve differential equations, partial differential equations analytically, rely on separation into the multiple dimensions and leading to the solution of ordinary differential equations. And these ordinary differential equations are going to be special ones, and we need to learn how to treat them, and we need to learn first how to understand them, what the nature of them are, and then how to go about solving them. So these special kind of ordinary differential equation is called the eigenvalue boundary value problem, and this is not to be confused with the eigenvalue problems that we posed algebraically for matrix systems that appear to have a trivial solution, but in essence they're the same. Essentially, it's a boundary value problem that is homogeneous, that has homogeneous boundary conditions, and therefore the obvious solution is a trivial one, is 0. But there's a very specific set of particular values for which that equation, that boundary value problem, governing equation and boundary conditions, has a non-zero solution, and we call that an eigenvalue problem as well. So let's pose this. So this is modeling methods in ME, and again, this is a new section in the semester, and we have been discussing up until this point the application of ordinary differential equations and the solution methods, both analytical and numerical. Now we're going to jump into partial differential equations, and again, before we do that, we're going to talk about eigenvalue boundary value problems. These are, again, special ones. Now, why are we going to shift focus to partial differential equations? Well, obviously, in engineering and sciences, many phenomena are governed by partial differential equations. Those differential equations, whose field variable, whose dependent variable is a function of more than one parameter, more than just single space quantity or space parameter, or more than just time. It can be time and space, or it can be multiple dimensions in space, or it can be both, multiple dimensions in space and time. So eigenvalue boundary value problems are special ordinary differential boundary value problems, BVPs, whose solutions only exist for specific characteristic values. So instead of trying to define these more formally, let's just go to an example so that we understand what this means. So given the following BVP, boundary value problem, that, remember, is comprised of a governing equation, and in this case let's just talk about these very simple second order ODE, and as you can see is homogeneous, and the boundary conditions, I'm going to give you a simple set of complete boundary conditions, one at x equals 0 and make it equal to 0, and one at x equal L, and we're also going to make it equal 0, and as you can see, these are also homogeneous. So obviously the solution of this problem is y equals 0, because y equals 0 both satisfies the governing equation and simultaneously satisfies both boundary conditions. Obviously, that is a solution. That's an acceptable solution. But sometimes we need something that's different than 0. So for this particular one, a solution to this VVP, boundary variable problem, is yx equals 0. It's a trivial one. However, we may need a non-trivial. We may need a non-trivial one, and well, we might need it for different reasons. And as I explained already, when we look at solutions of partial differential equations, we're going to break those partial differential equations into pieces that become ordinary differential equations. And in order for the methodology to work, we need these pieces not to be trivial solutions, not to have trivial solutions. So we need to seek specialized solutions that are specific for characteristic values that would make these a non-trivial solution. So how is that even possible? We have an equation, we have boundary conditions, and we have the solution. This is a linear equation. This is a set of well-posed linear boundary conditions, and there has to be only one possible solution. That's what the theory says, and that one possible solution is 0. So how is it possible that I'm going to get something that is different than 0? Well, let's see. Now, the solution to this problem the general solution to the second order constant coefficient ordinary differential equation, we can find the roots of this equation. You see you have a, b is equal to 0, a is equal to 1, b is equal to 0, c is equal to lambda square. The roots are going to be plus and minus lambda I, and therefore obviously the solution is imaginary. The roots of the initial equation are imaginary, and therefore the solution, the general solution, is going to be in terms of cosines and sine. We've already gone through this, and we know that that is the solution to this equation. You can try it. You can differentiate these twice and plug it in here, and you'll see that this one cancels out with this one, and you get a 0. So that's the solution to the differential equation. So let's look at the boundary conditions. So at x equals 0, the boundary condition says it's homogeneous. The y has to be equal to 0, and therefore a times the cosine of 0 plus b times the sine of 0 must be equal to 0. From here, remember the cosine of 0 is equal to 1, while the sine of 0 is equal to 0. So you can, the b goes away obviously, and you get a is equal to 0. A is equal to 0. So that is the first determination of a constant of integration using one of the boundary conditions. So what we have so far is y of x is equal to b times the sine of lambda x. That's what we have so far. We are yet to apply the second boundary condition. Now let's do that. So at x equal L, we also know that the condition that is given to us is that y is equal to 0. So y is equal to 0 at x equal L. That means that b times the sine of lambda L is equal to 0. So now we have this. B times the sine of lambda L has to be equal to 0. So in order for this product to be equal to 0, either of these two things have to happen. Either b is equal to 0, or the sine of lambda L has to be equal to 0. Now, if we want a non-trivial solution, we cannot allow this to happen because we already determined that a is equal to 0. If we say that now that b is equal to 0, then the whole solution will go to 0, right? So y will be equal to 0. We're back to square one, a trivial solution. So this leads to a trivial solution. So our only choice will be this one. That's the only one that could potentially lead to a non-trivial solution. So it basically says that sine lambda L should be equal to 0. That means that lambda L. All right, so if the sine of lambda L is equal to 0, the only way for that to happen is if lambda L is equal to the arcsine of 0. Right? And that means that lambda L should be equal to either 0, pi, 2 pi, 3 pi, so on and so forth, so that lambda L is equal to n pi, such that n is equal to any integer from 0 to infinity, right? So these are the values of, these are the times when the arcsine of 0, or the angles whose sine is equal to 0, right? So that would be 0, pi, 180 degrees, 360, and so on and so forth. Every rotation. So basically, what we can determine from these is that lambda, which we can now index with n, is equal to n pi over L. Such that n goes from 0 all the way to infinity. Integers, right? And these here are called the eigenvalues. These are the very specific values for which this particular equation would have a non-trivial solution. Only if those values of lambda happen to be multiples of pi over L. Only when lambdas are multiples of pi over L, this equation could potentially have non-zero solutions. So basically, what we get is that y of x is equal to b times the sine of lambda nx, where lambda n we already shown that it's n pi over L, and this we call xi n of x, the sine of lambda nx. This particular part of the solution here is the eigenfunction. Or eigenfunctions, because there's multiple ones, right? So basically, sines of different frequencies will actually satisfy this particular equation and set of boundary conditions. Again, how is that possible? Because if you look at what these functions look like, and let's say, which are valid for any value of x from minus infinity to infinity, but let's look at on the positive spectrum here, from x equals 0 to x equal L, then you'll see that you have a solution at lambda at n equals 0, lambda n is equal to 0, so you have sine of 0, which is 0. So lambda 0 is just, or psi 0 is just this, psi 0 of x. Then when n is equal to 1, you have pi over L. You basically have the sine of pi over L times x, and that, if you plot, will look like this. So this will be psi 1 of x. See, it satisfies the boundary condition. It's equal to 0 here, and it's equal to 0 here. And it also satisfies the equation, the governing equation. At n equal 2, you have 2 pi over L, then you have the sine of 2 pi over L times x, and if you plot this, you just get the sine with twice the frequency. So this is psi 2 of x. And then you have an infinite number of them. So there's an infinite number of overlapping solutions that satisfy the given boundary value problems, as long as the parameter lambda happens to be that. So those are the eigenvalues, the very specific set of values for which there is a non-trivial solution. All right. Now let me give you another example. What if we change the boundary value problem given the following boundary value problem, where the governing equation looks almost identical to the previous one. It's just that we have a minus sign, and the boundary conditions are the same. So we have a set of well-posed governing equation and boundary conditions. They're all homogeneous, and therefore the solution apparently is trivial. The solution is equal to 0. Let's see if we can find a non-trivial solution. Let's see if we can make up an eigenvalue problem out of these. General solution. Okay, so if we pose the initial equation from these, and where a is equal to 1, b is equal to 0, c is equal to minus lambda squared, find the roots of that, we'll find that the roots m1 and m2 are equal to plus minus lambda, and therefore this is an exponential solution, and you can write the exponential solution instead of using the exponential function. You can use the hyperbolic trigonometric functions, or hyperbolic functions like this, which is perfectly equivalent. It will be the cosine hyperbolic of lambda x and the sine hyperbolic of lambda x, obviously separated or linearly combined with two constants of integration a and b. Let's impose the first of the two boundary conditions at x equals 0, y is equal to 0, so it's a times the cosine of 0 plus b times the sine of 0. This is 1, this is 0, and therefore what you get out of these is that, again, a times 1, b times 0, a times 1 is equal to 0, then a is equal to 0. This is what you deduce from imposing the first condition. So now we got rid of one of the constants of integration. The second one, so what we're left with is y of x is equal to b times the sine hyperbolic of lambda x. We're in the same route as before. And the second boundary condition, y at L is equal to 0, basically says that b times the sine hyperbolic of lambda L should be equal to 0. So again, we have a product. That product has to be equal to 0. And therefore you have one of two choices. Either b is equal to 0, which we know will lead to a trivial solution, because now both a and b are equal to 0, so x equals 0, or the sine hyperbolic of lambda L is equal to 0. So when is the sine hyperbolic of lambda L equal to 0? Well, try to look it up. This is not possible. We cannot get the sine hyperbolic to be equal to 0 for any value of lambda, for any value of L, right? Unless lambda and L are actually not even for infinity or minus infinity. It will be an indeterminate number. So the sine hyperbolic will never be 0. So what we do, other than a lambda equals 0, that's it. So basically, the only option here is that b is equal to 0. And this will lead to y of x is equal to 0. And that's it. That's the only possible solution. So we have a trivial solution. And this is not an eigenvalue problem. So we cannot construct an eigenvalue problem out of these boundary value problem, just because of the minus sign. So eigenvalue problems are inherently oscillative. In order to be able to come up with a very specific set of solutions that are non-trivial, that are non-zero, which satisfy a homogeneous boundary governing equation and a set of homogeneous boundary conditions, the solution somehow has to oscillate around the x-axis. Otherwise, we cannot come up with it. So having that minus sign in the equation leads to positive roots, or real roots, which will make up exponential solutions, and therefore that would not actually satisfy what we're looking for. So where do we go from here? So if we have an equation with a minus sign, we know it's not going to work as an eigenvalue problem. So if we're hoping to construct problems that have non-trivial solutions out of bigger problems, then we have to be sure and we have to be careful as to make them possible eigenvalue problems. Now, one important property of eigenfunctions and this is also going to be a key piece in the solution of partial differential equations, is that they obey what's called orthogonality. And what is this? It basically is a property that says that if you have an eigenfunction xi, you can take one of those eigenfunctions, psi n, for example, or one of the frequencies, and then take another eigenfunction, well, the same eigenfunction, but at another frequency, so we call it xi m, and then we multiply it by what we call a weight function, and integrate them over the span a to b, which is where they're valid. That could be 0 to L in the cases that we're working on right now. That can lead to two possible solutions, either 0 if n is different than m, or some number f or some value f if n is equal to m. So that is called orthogonality. These eigenfunctions integrate to 0 when you multiply them to each other with a weight function, if they are at different frequencies, and they only integrate to a non-zero value if the frequencies are the same. Where, actually, let's frame this, because this is a very important property which will be essential to making our solutions methods work from this point on. And we'll see how we implement that next class. So where a to b is the range of the eigenfunction. So obviously the eigenfunctions are smooth, continuous functions that are valid between minus infinity and infinity, but in our problem, in our boundary value problem, they will be useful in a specific range from 0 to L, or from a to b. And omega x, or wx, is a weight function. So it is said that xi n is orthogonal on a to b with respect to wx. That's how you read this equation. Now let's look at an example. So we've already determined that the sign of lambda nx, such that lambda n is equal to n pi over L, is an eigenfunction. And it's an eigenfunction that is valid from 0 to L. Is an eigenfunction. Again, these are the eigenvalues. This is the eigenfunction. We already determined that because you just solved the eigenvalue problem that led to that solution. That was a very simple problem with the boundary conditions at x equals 0 and at x equals L. Now let's show that xi n is orthogonal on 0 to L with respect to wx equal 1. So the weight function of this particular eigenfunction, I'm telling you, is equal to 1. We don't know where that comes from yet, but just trust me, the weight function of this one is equal to 1. So basically, what we're going to try to determine is this integral that's supposed to be indexed by n and m from 0 to L of psi n of x, psi m of x, wx dx. And by the way, these functions could potentially, or whatever value, and we should actually call this I and m. Okay, I and m, because it could potentially be a function of the subscripts n and m. And for this particular case, we are told that for these eigenfunction, the weight function should be equal to 0. So I and m is equal to the integral from 0 to L of the sine of n pi x over L times the sine of m pi x over L dx. And we are to show that that's should be equal to 0. Now, how do we do that? Well, we can do this a couple different ways, but I'm going to leave that up to you. If you take integrating by parts twice, you can very easily show that I n m is equal to 0. Except when n is equal to m, and I'll show that in a minute. So you take these, and you pick u, and you pick this one as dv, then you integrate by parts, so that's equal to u times v minus the integral of v du, so you calculate the integral of these and the derivative of these, and that's the second integral. And then you do it again, you integrate by parts again, pick u and dv consistent with the previous selection, and then you isolate the solution I and m. You'll notice that after you integrate twice by parts, the last integral that will show up is equivalent to this integral here, and you'll get 0 out of that. So I'll leave that completely up to you, but it's very easy to show. Now, if we make n equal L, if n is equal to m, then I n m, and I'm going to call it nn now, is the integral from 0 to L of the sine square of n pi x over L dx. And what we're going to do is use that identity that we commonly use. It says that sine square is 1/2 minus 1/2 of the cosine of twice the angle. So this integral right here should be equivalent to saying the integral from 0 to L of 1/2 minus 1/2 of the cosine of 2n pi over L times x dx. And then we can solve this integral very easily. This will be x over 2 minus 1/2 of the sine of 2n pi over Lx divided by 2n pi over L. And we're going to evaluate this from 0 to L. All right, so INN is equal to, well, when we evaluate the first term here on this solution, at L we get L over 2, the second one we get 0, so this will be L over 2 minus 0, and the other one would be 1/2 of the sine of 2n pi divided by 2n pi over L minus 1/2 of the sine of 0 divided by 2n pi over L. All right, so it's L over 2 minus 0, and then the sine of 0 we know is 0, and the sine of 2n pi, remember that n is an integer number, that's what the eigenvalue came from. So it would be the sine of 0, the sine of 2 pi, the sine of 4 pi. So it's 0 degrees and multiple revolutions of it. That's always 0. The sine of 0 is 0, and the sine of 2 pi is 0, and that's always 0. So basically, INN is equal to L over 2. So we found a solution that is not 0 to that integral, and it only occurs when the frequencies of the eigenvalues match, or the eigenfunctions match. So INM, which is the integral from 0 to L of the sine of n pi L over x times the sine of m pi L over x dx is either equal to 0 if n is different than m, or L over 2 if n is equal to m. So thereby satisfying the orthogonality property. There we go. So the function psi n equals sine lambda n x, such that lambda n is equal to n pi over L, is orthogonal on 0 to L with respect to the weight function 1, which is the one that we use to integrate. There's nothing in here. So we demonstrated that. All right. So, well, it turns out that eigenvalue problems are not just confined to these very simple ones that look like this. Very simple second order ordinary differential equations with constant coefficients. In fact, there's an entire family of eigenvalue problems. There's an infinite number, technically, of eigenvalue problems that we can construct. I'll go to a new page because this is sort of a subheading on what we're doing. So all eigenvalue problems can be generalized into a class called the Sturm, this is an R, Sturm, Liouville. There's a new U again, Liouville, Sturm, Liouville problems. And what are such problems? Well, is those whose governing equations go like this: p of x d xi dx plus some function qx plus omega x times lambda square psi of x is equal to 0. So it's governed by a second order equation, which can potentially have a first order term. So here, depending on what p of x is, you could potentially have you do chain rule this, then there's a first order term. And there are some functions there that could potentially make these a variable coefficient second order equation. And boundary conditions are dictated by they have to be linear. So this is a linear equation, and the boundary conditions also have to be linear, but they can be of any type, as we have explained before. Boundary conditions could either be the first kind, second kind, or third kind. So at x equal a, it doesn't have to be 0. You can have this combination of either first kind, second kind, or third kind if both a1 and a2 are different than 0. And it has to be homogeneous, it has to equate to 0. And also a2, I'm sorry, I'm going to call it b1, d psi dx at x equal b at the other side of the domain times b2 psi of b must also be equal to 0. So you have to have a homogeneous second order equation, linear, could be variable coefficients, and you have to have a complete set of boundary conditions at x equal a and at x equal b. Any kind, first, second, or third at x equal a, any kind, first, second, or third at x equal b, but both have to be homogeneous. So homogeneous governing equation and boundary conditions. Okay, these boundary value problem has solutions in terms of eigenfunctions psi n of x with eigenvalues lambda n, and the eigenfunctions are orthogonal on the range x from a to b with respect to this weight function wx. So it will be a matter of solving these equations. So you can pose your equation, you can come up with a function p and a function q, come up with your own equation, and if you can find a solution for it, if it's variable coefficient, obviously you not have to do a serious expansion and try to get it there. But let's see a couple of examples of some of these eigenvalues who are going to be useful in the solutions of partial differential equations, and you'll see how that works. But again, the only reason that we are continuing talking about ordinary differential equations, even though we just closed that segment of the semester, is because this is a crutch to be able to solve partial differential equations. And in order to get there, we need to be able to deal with these eigenvalue problems. So let's look at an example. The same equation that we dealt with before, with which we dealt. There it is. And now the boundary conditions is going to be slightly different. I'm going to say that dy dx at x equals 0 is equal to 0, and that y at x equal L is equal to 0. Again, both conditions are homogeneous. It's just that I have a second kind condition at x equals 0 and a first kind condition at x equals L. On one side we impose the slope, and on the other side we impose the value. Now if we take this and compare, or comparing to Sturm-Liouville problem. Sturm should be capital S. So we're going to take this and try to compare it to that one. See the equation would be 1 for which P is equal to 1, Q is equal to 0, and W is equal to 1. So this is the same as this. It can be actually framed into the Sturm-Liouville class of problems with Px is equal to 1, Qx is equal to 0, and Wx is equal to 1. Great. Now how do we go about solving this problem? And by the way, we can also frame the boundary conditions. If we look at the Sturm-Liouville problem, the boundary conditions is a combination of these parameters a1 and a2 at x equals 0 and parameters b1 and b2 at x equals b. And if we compare it to these, we're basically saying that a1 is equal to 1 and a2 is equal to 0, while b1 is equal to 0 and b2 is equal to 1. So the condition at x equals 0 is called a natural condition. So when we impose a slope, we're saying it's a natural condition, second kind, or Neumann boundary conditions. And here on x equal L, we're saying, so this is at x equals 0, and this one is at x equal L. So this will be A and B. This is called a forced boundary condition, also called a first kind boundary condition, also called a Dirichlet boundary condition. Okay, there's 3 names for the same thing. All right, the general solution. Y of x is equal to A cosine of lambda x plus B sine of lambda x. Okay, so far everything looks identical to the problem that we already solved. It's just that when we impose the first condition at x equals 0, and given that it's a homogeneous condition, it's equal to 0, the derivative of these is minus lambda a sine lambda x plus b lambda, or lambda b cosine of lambda x. And this will be at x equal 0, and this will be at x equal 0. So this will be 0 is equal to minus a lambda times the sine of 0, which is 0, plus lambda b times the cosine of 0, which is 1. So that means that b is equal to 0. This one will go away. So this will all go away, and we just get that b is equal to 0. So right off the bat, we're left with y of x is equal to a cosine of lambda x. We're left with a different eigenfunction. Not the sine, but now the cosine. It's okay. The cosine can also be an eigenfunction. The cosine is also a function that oscillates. The cosine is also a function that can satisfy equation and boundary conditions. And it's also a function that could be orthogonal to itself. Now let's impose a second condition, the one that says that YL is equal to 0. That would be a cosine of lambda L. That means that either a is equal to 0 or the cosine of lambda L is equal to 0. So we know that we cannot use this because that will lead to a trivial solution, and we have to use this. So the cosine of lambda L must be equal to 0, implies that lambda L has to be either pi over 2, 3 pi over 2, 5 pi over 2, etc., etc., etc. So it's just multiples of 90 degrees. 180 degree turn after 90 degrees. So pi over 2, then 270 degrees, then back to 90 degrees, and so on and so forth. For those values of lambda L, then this equation has a non-trivial solution, or this boundary value problem has a non-trivial solution. So essentially, lambda n is pi times 2n plus 1 divided by 2l. These are the eigenvalues. And the resulting eigenfunction is that psi n x is equal to the cosine. Well, we already found that. The cosine of lambda n x. There we go. So slightly different than before. Instead of the sine, we got the cosine, and instead of n pi over l, we got these multiples of pi over 2. So just because one of the boundary conditions changed, and I guarantee that this eigenfunction is orthogonal to itself. You can try it and find out what the solution is. All right, so you see that by just basically changing something slightly, one of the boundary conditions type, we didn't change the boundary condition value, still 0, but we just made it from a first kind to a second kind. The eigenfunction changed completely from a sine to a cosine, and the eigenvalues changed completely from multiples of pi to multiples of pi over 2. So let's see what happens when we change the equation itself. Let's do another example here of another problem that we can frame within the class of Sturm-Liouville problems. And we're going to say this example. We're going to go to an old known equation, which is a Bessel equation of order nu. Okay, we learned about these Bessel equations before. We also learned that the solution of the Bessel equation of any order leads to oscillative solutions, right? Solutions that actually cross the x-axis infinite number of times. However, they don't do it. They do it periodically, but they don't do it at a uniform period. The frequency increases as x increases. So these Bessel equations, the generalized Bessel equation of order nu is x squared, the second y dx squared plus x dy dx plus m squared x squared minus nu squared y of x is equal to 0. Okay. All right. So we learned that this equation, known as the Bessel equation of order nu, has a solution in terms of Bessel functions of the first kind and the second kind, which is kind of akin to sines and cosines, or cosines or sine, but slightly different. Now we can rewrite this equation as d dx x dy dx plus m squared x minus nu squared over x y of x is equal to 0. So see what I did is I divided everything by x, right? And then I took x here and plugged it in into into this equation, into this derivative, and now it would just, if you expand this and chain rule it out, you get exactly the same equation. If you expand this and multiply it by x, you get exactly the same equation. All right, so if you compare these, comparing to Sturm-Liouville problem, so I'm going to go back and see, well, what are the similarities between that one and that one? Well, it looks exactly the same. Px is equal to x, then omega x is equal to x, lambda square is equal to m square, and q of x is minus nu square over x. Okay, so let's put that together and say that this is the same thing as this Sturm-Liouville problem, where px is equal to x, qx is equal to minus nu square over x, and wx is equal to x. Also, lambda square is equal to m square. Okay, so if you compare this one to this one, lambda square is equal to m square. In the Sturm-Liouville problem, we call it lambda instead of m. The eigenfunctions of this problem, xi n of x, are either the Bessel function of the first kind of order nu, or and this Bessel function of the second kind of order nu. The same way that if you had the problem that we just solved before, you would sometimes get the sine, sometimes get the cosine, or sometimes you get a combination of the two, depending on the combination of boundary conditions. So you get either this one, or the two, depending on the combination of boundary conditions. Again, analogous as to how sometimes you get the sine, sometimes you get the cosine, and in cases that we didn't look at, but it will work out, that sometimes you get a combination of the two. Now, what are the eigenvalues of this problem? With lambda m, the eigenvalues, being the roots of the Bessel function, either the first kind or the second kind of order nu, the nth root. So this is the nth root of the Bessel function of order nu. Okay, and in addition to that, we get that these functions are orthogonal from A to B, A being the beginning of the domain, B being the end of the domain. This function, whatever they are, either J, Y, or the combination of the two, they are orthogonal to each other, meaning that if you integrate them at different frequencies with a wave function of x, because that's what comes out directly out of the equation when comparing it to the Sturm-Liouville problem, you either get a 0 if n is different than m, or you get an INM, some number, some non-zero value for that integral when n is equal to m. And that's how it works also for the Bessel equation. It turns out that you can frame the Legendre problem also in the same exact way. You can frame all kinds of problems that are useful for solving partial differential equations when you break them up into smaller pieces and break them up into ordinary differential equations that can be framed into the Sturm-Liouville class of problems, and therefore, or thereby, leading to eigenfunctions and eigenvalues and leading to this orthogonality principle or property that will be very, very useful and as the final piece to solving those partial differential equations, as you'll see next class. So that's all I wanted to go over today, and thank you for your attention, and I'll see you next class.